Our sun is a star, a giant ball of burning gas. It's not a static, unchanging object. It pulsates with energy, following a fascinating rhythm, the solar cycle. This cycle, averaging about 11 years, dictates the sun's activity level, much like a heartbeat dictates the rhythm of life. Imagine the sun as a cosmic drummer, setting the tempo for the solar system. Sometimes the beat is calm and steady, marked by a quiet sun. This is solar minimum. At other times, the drums pound with intensity as solar maximum unleashes a flurry of solar flares and coronal mass ejections. This isn't some random cosmic performance. Understanding this 11-year cycle and the dramatic shifts between solar minimum and maximum is key to understanding the sun's influence on our planet. The sun's heartbeat, its 11-year cycle, is a fundamental rhythm of our solar system. By studying this cycle, we gain a deeper understanding of the sun's influence on our world and the vast expanse of space around us. Imagine a wave, cresting high and then receding. This imagery captures the essence of the solar cycle. At its peak, solar maximum is a time of heightened solar activity. Sunspots, dark, cooler regions on the sun's surface, proliferate. Solar flares, sudden bursts of energy erupt more frequently. Coronal mass ejections, massive expulsions of plasma and magnetic fields blast into space. Then comes the trough, solar minimum. Sunspot activity dwindles. Solar flares and coronal mass ejections become less common. The sun's surface appears calmer, less turbulent. These shifts, from the energetic highs of solar maximum to the quieter lows of solar minimum, are driven by the sun's magnetic field. Like a tangled, invisible web, this magnetic field undergoes a complete flip every 11 years. Marking the peak of each solar cycle. Understanding these rhythmic changes is crucial. They hold the key to predicting space weather, the conditions in space that can impact our technology and astronauts. Scientists use a variety of tools and techniques to track and predict the sun's activity. One key indicator is the number of sunspots. More sunspots mean more solar activity. Imagine these sunspots as telltale signs on the sun's surface, revealing its internal magnetic turmoil. By carefully counting and mapping these spots over time, scientists can chart the progression of the solar cycle. But there are other clues as well. Spacecraft, like vigilant sentinels, constantly monitor the sun, capturing images of solar flares and coronal mass ejections. These images provide valuable data on the strength and direction of these solar storms. By analyzing this wealth of data, scientists can develop models to forecast solar activity, much like meteorologists forecast the weather here on Earth. These forecasts are crucial for protecting our technology and astronauts from the potential hazards of space weather. Earth has a front-row seat to the sun's dramatic performance. While our planet's atmosphere and magnetic field act as shields, protecting us from the most harmful radiation, the impacts of the solar cycle are still felt. During solar maximum, the increased solar radiation and charged particles can disrupt satellites, causing communication and navigation problems. Imagine, if you will, a sudden blackout of your GPS or satellite TV, all thanks to a solar storm. These storms can also disrupt power grids, leading to widespread blackouts. In 1989, a powerful solar storm caused a major blackout in Quebec, Canada, leaving millions without power for hours. But the solar cycle also gives us something beautiful, the auroras. These dazzling displays of light in the sky, often seen near the Earth's poles, are caused by charged particles from the sun interacting with our atmosphere. Predicting solar storms is a bit like predicting the weather, only on a much grander scale. There are inherent uncertainties, but scientists are constantly refining their forecasting models, using data from spacecraft and ground-based observatories. Imagine a network of space buoys, strategically positioned to detect incoming solar storms. That's what our current fleet of spacecraft is like, providing us with valuable lead time to prepare for potential impacts. The goal is to improve our forecasting accuracy, giving us more time to protect our technology, astronauts, and power grids from the sun's occasional outbursts. Just like we check the weather forecast before leaving the house, someday we may routinely check the space weather forecast. As our reliance on technology grows, so too does the importance of understanding and predicting space weather. The future of space exploration, satellite communication, and even our power grids depends on it. The sun's 11-year cycle is a powerful reminder that we live in a dynamic and interconnected solar system. Just as the sun's gravity holds our planet in its orbit, its magnetic field and energetic outbursts influence our world in profound ways. By studying the solar cycle, we gain a deeper appreciation for the sun's influence on our planet, from the air we breathe to the technology we rely upon. It's a humbling reminder that we are not just Earthlings, but citizens of a larger solar system. As we continue to explore the cosmos, understanding the sun's rhythms will be crucial for safeguarding our future explorations and ensuring the well-being of our technological civilization here on Earth. The sun's story is far from over, and we've only just begun to unravel its mysteries.